So for example, in the circuit that we just finished analyzing, we had a battery, a resistor, another resistor, right? This was junction A and this was junction B, right? How many junctions do we have in this circuit? Two. So we can only write one useful junction rule. Why? Because suppose I didn't know the value of this current, and I called it I1, and I call this one I2, and I call this one I2. If I consider junction A, the sum of the currents going in equals the sum of the currents going out. So what would I write down as my formula relating those three currents?
You'd say I1 equals I2 plus I3?
Exactly. But if I consider junction B, the sum of the currents going in must equal the sum of the currents going out, right? So, well, I2 comes in, right? I3 comes in, and I1 must be coming out. So what should I write down? What are the currents going in? And what is the current going out? Junction B. And this equation is the same as that. So only one of them was useful. Okay? So if there's a circuit with 10 junctions, I can write 9 useful junction rules. If there's a circuit with 15 junctions, I can write 14 useful junction rules, one less. If there's a circuit with 3 junctions, I can write 2 useful junction rules. Okay, are we content with the junction rule? The sum of the currents going in must equal the sum of the currents going out. And I can only write so many useful junction rules. So many independent equations is what I should be saying. Because equation number 1 is not independent from equation number 2. In this case, they're the same. So there's only one useful junction rule that can be applied here because there are 2 junctions in the circuit. Okay, now let me spend more time on Kirchhoff's other rule. Okay? And this one is a statement not of conservation of charge, but a statement of conservation of energy. Remember when I said in this circuit that what if I choose the potential there to be 50 volts, right? Remember, I think I said 50 volts? Now, what if I take a trip around this circuit? What if I take a trip? If I go this way and come back to that point, by how much did the potential change? Nothing, because I went back where I started, right? What if instead I went this other way? By how much did the potential change?
Here.
Nothing, because I ended up where I started. What if I went this way? All the way around and get there. By how much did the potential change? Nothing. What if I went the other way around? What if I went this way? By how much did the potential change?
Not at all.
By nothing. Yes? In other words, the potential difference between, it's like I'm calculating this. The potential at A minus the potential at A, well, it's gonna be 0 because I ended up where I started. Yes? Now, the question is, when we take a trip like that, how do we write the potential across a battery? And how do we write the potential across a resistor? Right? So, for the battery, it's simple, right? Or simpler, I should say, for the battery. When you go across a battery, it's simpler. Because what if I have a battery like this? And this is 10 volts. And I'm here. And I go this way. When I go from here to here across this battery, what's the potential difference across the battery? By how much did my potential change? By 10 volts, right? But what if I were here and I went the other way? By how much did the potential change when I go across the battery?
Negative 10 volts.
Negative 10 volts, because I went from higher to lower. Maybe the potential here was 70 volts, and so the potential here has to be 60 volts, so I dropped. So in that case, the potential difference has to be minus 10 volts. So if you go through the battery, from the negative to the positive, you went up in potential. Because the positive means it's at a higher potential than the negative terminal. But if when you go through the battery, you go from the positive to the negative, you dropped in potential, so you dropped in potential. So it's a minus, whatever the voltage is across the battery. Yes? Now, what about if you go through a resistor? What if there's a resistor like this, and the resistance is 2 ohms. Suppose the current is 5 ohms this way.
Yeah.
And here you are, and you go to this way to here. When you get there, what was the potential difference? You went from this point to this point. Did you go up in potential or did you go down in potential? Down in potential, because how do you know I went down?
It's in the direction.
In the electric field.
Because the current is to the right, and if the current is to the right, as if the positive charges go there, then correct, the electric field is this way. And if I go in the same direction as the electric field, I drop in potential. So following that path, I would write this as, well, 5 times 2 is 10, so this would be minus 10.
Wouldn't that be 5 amps?
Huh?
Wouldn't that be 5 amps?
No, I'm considering a drop in potential, so 5 times 2,
No, I'm talking, it says 5 ohms.
oh, 5 amps, yeah. Wrong label there. So that would be 10 volts. Minus 10 volts. But if I had the same circuit, right? 2 ohms, and the current is 5 amps to the right. But this time I went from here to here. Huh? If this is me going this way, right? Then I'm going to a location where the potential is some value to another location where the potential is bigger or smaller?
Bigger.
Is the potential here bigger or smaller than the potential there?
Larger.
Larger. So I went from this potential to this potential, so the potential difference is, well, I went up by 10 volts. So this is plus 10, and this would be minus 10. So what do you remember? Well, what is the voltage across a resistor? Ohm's law, I times R. The question is, do you write plus IR or do you write minus IR? So you just remember, if you move in the same direction as the current, it's minus IR. Because we label the direction of the current as being the direction of the electric field, as if the positive charges flow. And if you move through the resistor in the opposite direction of the current, then the potential difference is plus IR. So plus IR minus IR for resistors, plus IR if you go through the resistor in the opposite direction as the current, minus IR for the resistor if you go in the same direction as the current. For the batteries, it doesn't matter which way the current is. If you go from negative to plus, you went up in potential. If you go from plus to minus, you went down in potential. And soon, I'll show you how I deal with the internal resistance of the battery. I just think of it as another resistor in the circuit. I'll just show you, how that is. But these are, and then this is explained in my notes over here for Kirkland's laws. So the sum of the voltages across all the circuit elements in a circuit, notice, for a closed loop, it's gonna be a loop, because I gotta come back to where I started, then the sum of the potentials has to be zero, of the potential differences has to be zero. So the sum of the potential difference has to be zero, because you have a loop, any loop. I don't care if you start here and you go clockwise, or if you go counterclockwise, or if you go on the outside counterclockwise, or if you go on the outside clockwise, or if you go along another path, right? It doesn't matter. Any loop, if you close the loop, if you end up where you started, the sum of all the potential differences has to be zero, because you ended up where you started. You ended up at the same point where the potential is the same as the potential of that point when you started. And for resistors, so I say here, you move across the resistor. If you move in the same direction as the current, then you write the potential difference as I times R, but because you're going in the same direction as the current, then it's minus I times R. But if you move across the resistor in the opposite direction to the current, then the potential across the resistor, the voltage across the resistor is I times R by Ohm's law. Now you write it as plus IR. This I over here is not me, that I is the current. So that's why I say you. Right? Because I also, you is like you literally take a trip. But I don't want to say I because I don't want I to mean me taking the trip, but also I to mean the current. So plus IR if you travel in the opposite direction to the current through the resistor, plus IR if you travel in the opposite direction to the current through the resistor, and if you move in the same direction, if you travel in the same direction as the current through the resistor, then it's minus IR. So let's solve this problem, the simple circuit, again, using Kirkland's laws. Not resistors connected in series, resistors connected in parallel. Use a completely different approach. Okay? Let's use this more general method for solving problems. But before I actually solve this problem in detail, I'm gonna draw something crazy on the board. So don't bother writing it, because it'll be crazy. In fact, I haven't exactly decided what I'm gonna draw, but my attempt is to draw something crazy. Okay? So don't draw it. So what if you have a circuit like this? That wasn't supposed to look like that. Okay, something like that. So the voltage across this is delta V1, delta V2, delta V3, batteries. These are many batteries in the circuit, right? V4, delta V5, delta V6. I don't think and then this is R1, R2, R3, R4. Oh, I'm gonna put another battery here. So delta V, what? 7. So R5, R6, R7, R8. Right? Okay, crazy, a crazy circuit, right? First of all, how many junctions are there?
1, 2, 3,
6.
1, 2, 3, 4.
I only see 4.
Oh,
There's one right here, because you got 3 wires meeting or more. 2, 3, 4. Not a junction, not a junction. So 4 junctions. So how many useful junction rules would I write down? one less. So there are 4 junctions, 1, 2, 3, 4, right? Let's say A, B, C, D. I can write 3 junction rules, one less than the number of junctions. Now, how many different currents would there be in this circuit? I'm going to use red for that. How many? 7. I heard 8 and I heard 7. Well, how about we do it? You're gonna get one current over here, maybe that's I1. Another current along this path, that's I2. You'll get another one along this path, that's I3. And another one here, I4, I5, I6, and I7. So there are 7 currents. Which way are they? I'll say that this one is this way. I'll say that this one is this way. But that's a guess. I'll say that this one is this way. That's a guess. This one might be this way. That's a guess. This one I'll say is this way. That's a guess. This one, gee, I don't know. Maybe I'll say it this way. And that's a guess. And this one, I'll make it this way. That's a guess. They're all guesses. So, how many different currents are there? 7, right? So I gotta figure out 7 currents. So therefore, I need how many equations? So, 7 unknowns. Of those 7 unknowns, how many junction rules can I write? How many junctions are there? 4. So how many useful junction rules can I write? So I'm gonna write 3 junction rules. And then I'm gonna write 4 loop rules. And then I'm gonna have 7 equations for 7 unknowns. And then have fun with the algebra. A computer would be better, right? Yes? I'm not gonna put a problem like that in any, of the exams or, I don't want you to solve 7 equations for 7 unknowns. That's, just, you spend the whole 2 hours doing that probably. But, you have a circuit. As soon as I see various batteries, I immediately think Kirchhoff's laws. I mean, let me show you some problems in chapter 26. Some of the problems for which I wrote down solutions. See, this circuit over here, like that one, right? Let's just look at that one. This circuit, it's easy to see that these 2 are in parallel, and these 2 are in parallel, and then those 2 combinations will combine in series. Okay, so I can use series and parallels, right? And I have 1 battery. How about that one? I see I have 1 battery, 1 resistor. So these 2 are in parallel. I combine that with this one to make it in series. And then that combination is in parallel with this one. And I can solve that problem. Not bad. This one, same thing. This one is in parallel with that one, so I can combine them into one. Boom, boom, boom. Piece of cake. Now, look at this one. I got 2 batteries, and how is this resistor connected to this resistor and to this one? They're not in series and they're not in parallel either. For them to be in series, they'll have to be along the same line, so they have the same current. This is in a different segment, the 6 ohm, than that one, and this one. So they're not in series, and they're not in parallel either, because yes, on the right-hand side, all of them are holding hands. Right, so this potential is the same as that, is the same as that, but the potential here is not the same as the potential there, because you gotta go through this battery, and it's not the same as the potential there, because you gotta go through that battery. So they're not in parallel and they're not in series. This one, you only solve it using Kirkland's laws. You have to. How many junctions are in this circuit? Two junctions, right? So how many useful junction rules would you write? One. And the other, and how many different currents? So you got one here, two, and three. So you need three equations, but you can only write one junction rule. The other two will be loop rules. You can consider the whole loop around, or you can consider this loop, or you can consider this loop. You got three choices to choose loops. Any loop will do. As long as you don't repeat the loop, because then you'll end up with the same equation. Look at this circuit. Two batteries, this one, this one. Now, before I use the loop rules and the junction rules over here, I would simplify it and combine the 1 with the 6 in series. The 1 and the 4 in series, and the 1 and the 3 in series. But I would still have to do the loop rules.
We can still combine them even though there's
What's that?
We can still combine them even though they're surrounding batteries.
Well, because they're on the same line, so they'll have the same current. They're in series if they have the same. So this one will have the same current as that one, and this one will have the same current as that one because they're on the same line.
Okay.
So they'll have the same. You see, whatever. If you have one amp over here, that one amp has to make it through that one because there's no split.
Right.
That will happen. What about this circuit? Well, as soon as I say, 1, 2, 3 batteries, this resistor is in series with that one, but then it's not in series with this combination, and Kirkland's laws, right away. I gotta use the junction rule and the loop rule. What about this circuit? Same thing. This circuit, same thing. So how about we solve the problem that we solved earlier today using the junction rules, okay? And the loop rule and the junction rule, using Kirkland's laws. What I do? And you'll see which method is easier for that particular problem. So, this. Okay, so we have, this is the extra example revisited, right? So this was what, 12 volts? Is that what it was?
Mm-hmm.
This was 2/3 of an ohm. This was 0.8. I think this was 2 ohms. This was 0.8. And this was 4 ohms, right? So, how many different currents will there be? 3, correct. So I'm gonna say this is I1, that'll be I1, that'll be I1, and it's gonna split, and I'm gonna call this I2, and this other one is gonna go like this, and that'll be I3 going down over here, right? Which means I3 here, right? So I1, actually this is I2. So you have I2 here and I3. So I have 3 unknowns. By the way, those directions I'm guessing. How will I know when I'm done solving the problem if my guess was correct for the direction of the current? So the way that I'll know is this. When I solve for that numerical value for the current, if it comes out positive, so many positive amps, then it is in the direction that I guessed. If it comes out negative, suppose it comes out to minus 3 amps, then it's still 3 amps, but in the opposite direction that I guessed. So if my guess is good, it'll come out positive. If my guess is for the direction, if it's the opposite direction that I guessed, right, of what it should be, then the answer is going to come out negative. So I'll know at the end if I did it right or wrong. That's kind of nice. So I have 3 unknown currents. I need to find out I1, I2, and I3. So, find I1, I2, and I3. So my goodness, I gotta solve 3 equations for 3 unknowns. So how many junctions are there? 2. How many useful junction rules can I write down? 1. So I'm gonna start with the junction rule. Let's say junction A. The sum of the currents going in equals the sum of the currents out. So what are the currents going towards this junction? Going in? I1. And what are the currents leaving this junction A?
I2 plus I3.
Exactly. So that's equation number 1. I have one of my 3 equations already. Okay. Second one is going to be a loop rule. So that means the sum of the voltages around that loop has to be 0. Now, which loop should I choose? Which loop would you like me to go around? Would you like me to go around in here, on the left, on the right, or all the way around? It's up to you. You tell me. I only need 2 more equations. And I have 3 choices. I can use this loop, or all the way around. Which one? Which one? The first one?
Yeah.
Do you want me to go around clockwise or counterclockwise? Clockwise? Okay, so I'm going to write it like this. That'll be me. And I'll say number 1. So this will be loop number 1. And that would be me. Where would you like me to start? Does it matter where I start? It doesn't matter because I'm going to end up wherever I start. So how about I start in this corner? I'm going to go up and then I'm going to end up coming this way, right? So, as I go up, when I go across this battery, should I write plus 12 volts or minus 12 volts?
Plus 12 volts.
Plus 12. And then I continue. As I go across this resistor, the voltage is, by Ohm's law, the current times the resistance. So it would be I1 times 2/3. Should I write plus 2/3 I1 or minus 2/3 I1? I'm going to the right in the same direction as the current, so it should be
Minus.
minus, correct. And then I get to junction A, and I turn, so I go down. So what will be the voltage across this resistor? It would be
Minus.
I times 2I2, right? Should it be plus or minus?
Minus.
Minus because I'm going in the same direction as the current. And then I get to junction B, turn, and then I end up where I started. So this is 0. Now let me clean this up a little bit. This would be 2/3 I1 plus 2I2 equals 12. I don't like that third over there. So what if I multiply the whole equation by 3? So I'm going to get 2I1 plus 6I2 equals 36. And I can see that all the coefficients are even. On the right hand side is even. So what if I divide by 2? So I'm going to get I1 plus 3I2, right, equals 18. Did I do that right? Let's see. Yeah? Looks good, right? So that's equation number 2. So I need a third equation, another loop rule. So which other loop would you like me to choose? How about I choose this one here? And since I went clockwise over here, why don't I go around that one in the counterclockwise sense, just to make it more interesting, I guess. So that would be me, number 2. And where should I start? Well, how about I start over here? So there I am, and I go this way. So what should I write down when I go across this resistor? The current through it is I3, and the resistance is 4. So what should I write down? What is the voltage across that resistor?
Minus 4I4.
Minus 4I3, right?
Are you going the clockwise?
I'm going this way. Oh, I said counterclockwise. Okay, so I'm going to go around the other way. Okay, sorry. Let me stick to what I said. I should write it over here to remind me. That's number 2. Yeah, let me do that so that I'm consistent. So I'm going to go the other way. I don't have to. I mean, it's just, that's what I had said first, so I'll just stick to that. So when I go this way, and I turn over here, when I go through this one, what should I write down when I go through this resistor?
2/3 I1. I mean, my bad. 2 I1. I2.
Plus or minus?
Plus.
Plus or minus?
Plus.
I'm going this way, in the same direction as that current. Plus or minus? Minus. And then I continue my trick. Head to junction B, turn, go this way. And what do I write down when I go across this other resistor? That's me. Plus 4I3, right? And then I end up where I started, so all of that is equal to 0. So 2I2 equals 4I3. If I divide by 2 on both sides, I'm going to get 2I3, right? Is equal to I2. This equation is telling me, remember what we said? That the current through here has to be half, it has to be half of the current through that other one, because that one possesses twice the resistance. Well, I'm getting that result right here from Kirkland's laws. And the rest is math. Now I have 3 equations. So I'm going to write them all down. So I got I1 equals I2 plus I3. And I have I1 equals, no, plus 3I2 equals 18. And I have I2 equals 2I3. Right? Can you see that all of the 3 equations have I2 in them? So what if I solve for I2 over here? This is going to be 18 minus I1 divided by 3. And if I solve for I2 over here, oh, it's 2I3, right? Then I'm going to solve for I1. Sorry. They all have I2, so I'm going to solve for I1 here will be 18 minus 3I2, and I'm going to take it and plug it in here, and then I'm going to have it in terms of I2, and then I3 will be 1/2 of I2. Now I'm going to take this and I'm going to plug it in there, so that this equation only has I2 and I can solve for it. So I1 is 18 minus 3I2 equals I2 plus I3, which is 1/2 of I2. So 18 equals 3I2 plus I2 plus 1/2 of I2. So 3 plus 1 is 4, 4.5, right? So 18 equals 4. Let's see, this is 1/2. So 3 and 1 is 4, this is 4.5. I2. That's the same as 9/2, right? I2. So therefore, I2 equals 18 times 2 is 36 divided by 9. So I2 is 4 amps. I can take that now and plug it in here and get I3, which is half of that. So half of 4 amps is 2 amps. And since I can now go to equation number 1, I1 equals I2 plus I3. I2 is 4 amps, and I3 is 2 amps, so I1 is 6 amps. And I bet you these are the values that we found before. So we would have 6 amps over here. Six amps coming in, 6 amps over here, and it'll split into I2 and I3, and I2 was 4 amps, so that's this one, 4 amps, and this one was 2 amps. And those are the same results that we had before. Exactly the same results. This problem is easier, in my opinion, to solve using resistors in series, resistors in parallel. But there are circuits where you can't combine them in series or parallel, so you must use Kirchhoff's laws. Notice that all the currents, this one came out positive, this one came out positive, and this one came out positive. They're all in the directions that I guessed. You should do this problem again. Choose, deliberately make, switch one of these and do it again, and you'll see what you get. So, there's only one more thing to discuss in this chapter, really, but I'll discuss it on Wednesday. It has to do with internal resistance of the batteries, and I'll just show you how I deal with those. Oh, there's also the RC circuit, so I'll do that on Wednesday. So, let's see. Is Tom Tran here? No? How about Logan Lee? No? And if you came in late, let me know so that I can mark it present. And I'll see some of you, I guess, later today, right? Have a good day, everyone. Yeah, let me know so I can.